Welcome, nocturnal minds, aboard. Your learning journey starts now. So, we've been navigating the tricky waters of scientific prediction and probability. Now let's pivot to something equally fascinating, yet often misunderstood. What exactly is pseudoscience? It's that category of claims that really want to be taken seriously as science, but ultimately fall short. Think of it like a wolf in sheep's clothing, or maybe a snake oil salesman using fancy lab coats. But hold on, not everything that isn't science is automatically pseudoscience. You wouldn't call playing football or writing a novel pseudoscience, would you? Even if someone tried to study them scientifically or pseudoscientifically, the activity itself isn't inherently one or the other. So we're looking at a neat little triad: proper science, then non-science that masquerades as science artarta, and finally non-science that just is non-science. Like knitting or collecting stamps. Okay, so how do we draw the line between good science and bad science versus this whole pseudoscience thing? Let's take a simple example. Imagine a chemist accidentally contaminates a sample, reads the pipette wrong, and reports garbage data. Is that pseudoscience? No, it's bad science. The key here is the violation of scientific norms, sloppy work, cutting corners. Whether the result happens to be true or false is almost beside the point. Think about physicists who mess up their calculations, but by sheer luck, their incorrect math cancels out errors from a flawed theory, giving a correct final answer. Still bad science, right? They broke the rules of calculation. But here's the crucial distinction: breaking the rules of scientific practice doesn't automatically make your work pseudoscience. It's a necessary step away from good science, perhaps towards bad science, but not necessarily the leap into pseudoscience territory. So, the big question becomes, what specific combination of factors, what set of conditions truly defines pseudoscience? Alright, examples might help us get a feel for this. Martin Gardner, a legendary debunker, famously said pseudoscience is fuzzy, like a continuum with no sharp edges. He tried to map it out, though. At one end, stuff everyone agrees is bonkers: the Earth is hollow, or it was made 10,000 years ago. Then, slightly less weird, homeopathy, Scientology. Moving up, we hit controversial claims, things like God guiding evolution or pulling infinite energy from empty space. And at the far end, open conjectures by scientists, like maybe there are other universes or life started elsewhere. Notice the overlap. What's pseudoscience today might be controversial science tomorrow. The NSF report from 2006 listed a bunch of beliefs they considered pseudoscientific: astrology, UFOs, ESP, ghosts. You name it. But here's where it gets tricky. See, these lists are slippery. Take the NSF saying belief in UFOs is pseudoscientific. Well, literally speaking, that's not quite right, is it? There are definitely unidentified flying objects out there. Pilots, astronomers, they've seen things they can't explain. So, maybe the definition used is too narrow. Or perhaps the claim is interpreted differently. The report also calls clairvoyance pseudoscientific, defining it as knowing the past and predicting the future. Hold on a second. Do I know the past? Yes, yesterday happened. Do I predict the future? The sun will rise tomorrow. By that definition, aren't we all clairvoyants? It highlights how crucial interpretation is. And then there's history throwing curveballs. People once declared falling rocks from the sky pseudoscientific nonsense. Turns out meteorites are real, acupuncture. Once dismissed as pseudoscience, now there's plausible evidence for its effectiveness, even if we don't fully understand why it works. So, labeling something pseudoscience isn't always straightforward. So, if we can't easily list all pseudoscience, maybe we should ask, what kind of thing are we even talking about when we say X is pseudoscientific? Is it a single statement, like there's a monster in Loch Ness? Lakato's thought so statement could be pseudoscientific, even if it sounds plausible. Or is it about a whole theory, a web of interconnected ideas? Thagard leaned this way. Others argue it's more complex. Maybe it's the pairing of a theory with the evidence available at a certain time. Think about the flat Earth idea. For ancient people with their limited observations, believing the Earth was flat was perfectly reasonable science. But for us today, armed with satellites and circumnavigation, that same belief is pseudoscientific. See how context and evidence matter. Then there's the view focusing on behavior. Is the person approaching the claim scientifically, testing it rigorously, or are they just blindly accepting it despite contradictory evidence? Could you pseudoscientifically argue for general relativity? Maybe. If Fred says fairies told him it's true, he's behaving pseudoscientifically, regardless of the theory's actual merits. Finally, some focus on the group, the entire practice or community. Are they generally following scientific methods, or are they systematically flawed? It seems like a mix of these perspectives might be needed. Let's look at a concrete attempt to define pseudoscience. Paul Thagard's analysis from 1978. He proposed two conditions. First, the theory itself needs to be failing less progressive than alternatives, full of unsolved problems over a long time. Second, and this is key, the community of people working on it needs to be lazy or dishonest about it. They don't try to fix the problems, ignore attempts to compare it to other theories, and cherry-pick only the confirming evidence while ignoring the disconfirming stuff. What's nice about this? It acknowledges that what counts as scientific depends on the time period. What's pseudoscientific now might have been cutting-edge research once. And it focuses on behavior, not just the theory's content. But does it hold up? Two big issues. First, it requires alternative theories to compare against. What if a theory is just plain wrong, but there are no good alternatives yet? Thagard himself admitted biorhythms couldn't be labeled pseudoscientific initially because there were no strong competitors. But surely, biorhythms are pseudoscientific based on the evidence against them. Second, the evil scientist problem. Imagine a theory is failing, but 90% of its practitioners are actually trying hard to improve it. Then, bam, an evil scientist kills them all, leaving only the 10% slackers who fit Taggard's description. According to his definition, the theory suddenly becomes pseudoscientific because the practitioners changed. That feels deeply counterintuitive, doesn't it? If crafting a perfect definition proves elusive, maybe we should switch tactics. Instead of necessary and sufficient conditions, let's create a checklist of characteristic features, warning signs. Think of it like spotting red flags. Bunch, Lilienfeld, Hansen, and others have compiled lists like these. We see things like constantly inventing new excuses, ad hoc hypotheses whenever a theory is challenged, ignoring inconvenient facts or experiments, shifting the burden of proof onto the skeptics, relying on experiments nobody else can replicate, citing some guru as having special insight, overloading arguments with anecdotes instead of data, dodging peer review, failing to connect with established scientific knowledge, and using jargon that sounds impressive but doesn't mean much. The more of these traits a practice exhibits, the higher the likelihood it's pseudoscientific. Gleimer and Stalker even humorously outlined principles for building pseudoscience. Find some random coincidences, blame it on a grand cosmic plan, and ignore any pesky details. Safi added another angle. It's not just about having bad theories, but using methodologically flawed procedures specifically designed to avoid being proven wrong, like Freud sometimes doing with psychoanalysis. So, we've seen attempts at analysis and lists of features. Which is better? Analysis promises logical clarity. If you meet condition X, you are pseudoscience. Lists are fuzzier, probabilistic indicators. But there are deep worries about the whole project of analysis. First, it's notoriously hard. As Loudon pointed out, every proposed criterion for demarcating science has failed under scrutiny. Finding a perfect analysis for pseudoscience seems similarly doomed. Second, there is the philosophical paradox of analysis. If you already knew the meaning of pseudoscience, why bother analyzing it? But if you don't know the meaning, how can you possibly analyze it? It feels like a catch-22. Third, and perhaps most practically important, getting bogged down in defining pseudoscience can distract us from the real issue. Remember Alice claiming code fusion. Bob says pseudoscience. Alice could respond by arguing her evidence is solid, or she could argue Bob's definition of pseudoscience is wrong. The far more productive discussion is about the evidence, whether it supports the claim. Focusing on definitions can derail the actual scientific debate. This applies to real-world debates too, like whether intelligent design is pseudoscience. This leads us to Lauden's provocative claim, calling something pseudoscience is just emotional baggage. It's a way to express contempt, to shut down discussion with a label. He argues we should ditch the term and just talk about the evidence. Gordon adds a layer. Scientists often use the label defensively, feeling threatened by ideas that challenge their authority or worldview. Using pseudoscience aggressively might even reflect poorly on the scientist doing the labeling. Lauden's conclusion. Give up trying to draw a line between science and non-science altogether. Now I can see the appeal of being cautious. But maybe giving up entirely is too extreme? While it's true, we can't have a perfect universal definition. Recognizing differences between science and non-science, or science and pseudoscience, can still be useful. Understanding why relativity is science and ESP is pseudoscience helps us grasp how science works. However, the dream of a single powerful analysis that works for everything, that might indeed be beyond our grasp. Often people try to demarcate science using the scientific method, but philosophers like Feyerabend threw a wrench in that gear. He argued there's no single scientific method. Science uses whatever methods work whenever they work. Trying to pin down one rigid set of rules is like trying to nail Jell-O to a wall. History shows this constantly. New breakthroughs often broke existing rules before those rules were updated. So, what would Feyerabend say about astrology, a classic target of pseudoscience accusations? He critiqued a group of scientists who dismissed astrology, arguing they were unfair caricatures. He pointed out astrology has a long sophisticated history, and interestingly, there are real correlations between planetary motions and earthly phenomena like tree growth via solar activity. His point wasn't to defend astrology, but to caution against sloppy criticism. The lesson? Yes, pseudoscience exists and needs critique, but we must ensure we're not misrepresenting legitimate science or historical complexity in the process. For those interested in digging deeper into the world of pseudoscience, there's a wealth of excellent reading. Gardner's classic, Good, Bad, and Bogus is a must-read. Randy's Flim Flam offers sharp insights from a magician's perspective. Sagan's Demon-Haunted World is a powerful defense of scientific thinking. Shermer's Why People Believe Weird Things explores the psychology behind it. And for a contemporary battleground, check out the debates surrounding intelligent design, with Montan arguing it's not pseudoscience and Piglucci firmly placing it in that category. Still and Dryden also provide a fascinating look at the social dynamics involved in labeling something pseudoscience. Now let's shift gears completely and dive into reduction. This concept has deep roots in the 17th century mechanical philosophy. Think clockwork universe. Two core ideas causes only come from the past, and the behavior of things is explained by the interactions of their parts, ideally touching parts. Think heat has increased motion of molecules. But then came Newton's gravity, action at a distance. This freaked out the mechanists. How could bodies influence each other without touching? It took a while, but eventually, even action at a distance was accepted, paving the way for huge successes like thermodynamics and electromagnetism being reduced to mechanics or statistical mechanics. Biology also saw early reductionist ambitions, trying to explain life as mechanics. But modern physics throws a wrench in the works again. Relativity loves locality, interactions happening nearby. Quantum mechanics, however, revels in non-locality, spooky action at a distance like entanglement. This fundamental tension shapes the debate about reductionism today. Philosophical discussions of reductionism went astray for a while, getting bogged down in formalities, like whether terms needed to match exactly type, or just instances token type. Sarkar argues we need to refocus on substantive issues, what actually matters empirically. Forget the linguistic hair-splitting. What makes an explanation reductionist in a meaningful way? Two key substantive criteria emerge from this shift. First, hierarchy and compositionality, and second, multiple realizability. Let's unpack these. First up, hierarchy and compositionality. The basic idea is that the reducing theory provides a deeper, more fundamental explanation. But just having a deeper theory isn't enough for a strong reduction. We need a sense of parts, explaining wholes. Think of genetics. The genotype explains the phenotype. We model the genes hierarchically loci, alleles, and show how they statistically determine traits. This is a non-spatial hierarchy. But physics throws curveballs, especially quantum mechanics. With entangled particles, the whole system has a definite state, but you can't assign definite states to the individual parts. Their properties are hopelessly intertwined. No hierarchical reduction here. Schrödinger himself called entanglement the central mystery. If we add compositionality requiring the hierarchy to correspond to a physical arrangement in space, we get the strongest form of reduction, the original goal of mechanical philosophy. Spatial wholes explained by their spatial parts. But even here, challenges remain. Genetic hierarchies don't perfectly map onto DNA segments due to overlapping genes. However, molecular biology provides stunning examples satisfying this criterion. Explaining how hemoglobin binds oxygen changes shape based on its parts, or how bacteria regulate enzyme production through physical molecular interactions, not magic. Here, biology delivered the goods for reductionism. The second major criterion is multiple realizability. This is a big objection. Often one concept in the reduced theory mental state, say, corresponds to many different physical states or kinds in the reducing theory. Could this be a fatal flaw for reductionism? If we insist that successful reduction requires denying multiple realizability, then many paradigm cases of reduction collapse. Think about thermodynamics. A single macroscopic state like pressure and temperature corresponds to an astronomical number of microscopic molecular configurations. That's extreme multiple realizability, and yet we consider the reduction of thermodynamics to kinetic theory a massive success. So demanding the elimination of multiple realizability seems counterproductive. It appears reductionists should simply accept that multiple realizability is often a feature, not a bug, of many reductions, particularly statistical ones. Trying to banish it would throw the baby out with the bathwater. Historically, reductionism had this grand ambition: unify all of science under the banner of fundamental physics. Think Newton unifying heaven and earth, Maxwell unifying electricity, magnetism, and light. This unity dream seemed plausible. But reality bites. Thermodynamics, despite being reduced to kinetic theory, remains a vital separate field for engineers. Classical genetics, even after the molecular revolution, is still used daily in clinics. Many areas of biology continue to operate successfully with their own levels of description, even when molecular details are known. Wimsatt offers a clever twist. Reductions actually clarify the limits and proper use of the reduced theory. Knowing how thermodynamics fits into kinetic theory tells us precisely when and how to apply it. Far from erasing disciplinary boundaries, successful reductions often reinforce them, encouraging the continued use of specialized theories within their appropriate domains. The assumptions needed to make the reduction work often highlight where the simplified theory breaks down. Here's another wrinkle. Reductions rarely work out as neat, purely logical deductions. They often involve approximations, idealizations, and empirical assumptions that go beyond the reducing theory itself. Think about deriving classical mechanics from special relativity by taking the speed of light to infinity. That's mathematically simple, but physically absurd. It requires changing a fundamental constant. Einstein's own derivation of Brownian motion relied on specific approximations. Boltzmann's famous derivation of the second law of thermodynamics depended on an assumption about molecular randomness. These aren't just minor fudges, they're crucial. What does this mean? It means reductions are often tentative, context-dependent, and rely on empirical assumptions that might not strictly follow from the reducing theory. This undermines the idea that reduction automatically justifies eliminating the entities or concepts of the reduced theory. It suggests the picture of unified science through simple derivations is overly simplistic. Despite these complexities, reductionism has been an incredibly powerful research strategy throughout history. Assuming that phenomena can ultimately be reduced drives inquiry. Even experiments in classical genetics, which seem purely observational, implicitly assume a genetic level explaining the phenotypic level. But we shouldn't worship at the altar of reductionism. Wimsatt pointed out how a bias towards reductionism led to flawed research in evolutionary biology, favoring explanations at lower levels. And modern techniques like massive data mining in genomics often produce results that don't easily fit a neat reductionist narrative. The takeaway? Reductionism is a valuable heuristic, a powerful tool, but not the only tool. A pluralistic approach to research, exploring diverse strategies that lead to empirically adequate explanations, is likely the wisest path forward. For those wanting to explore reductionism further, Wimsatt's work is foundational, especially his 1979 paper. Sober's edited volume covers key issues in evolutionary biology. Sarkar provides an extensive treatment focused on biology. Batterman delves into the complexities within physics. And the Wimsatt and Sarkar survey offers a good overview of recent developments. And finally, a quick note on acknowledgements, as per the original text. The author expresses gratitude to the editors and reviewers who helped refine this work. That concludes our detailed exploration of these fascinating topics.